Hi gang, Math 5500. The title, as you can see, Intro to Correlation and Regression with R. Um, so just to follow up on the previous video where we looked at means and some box plots and stuff, I want to focus more on using R for correlation and regression analysis. This is going to be it for the simple linear regression case. Simple linear regression just indicates that you have one predictor. We will move into multiple regression soon enough. On my desktop, you can see that I have a data set body fat. You should have access to this data set in lesson one. So just as a review, I'm going to get my working directory. Okay. Wow, this is starting out great. My working directory is just is not set, so I want to set the working directory. And I want to set it to my desktop so I can retrieve the dataset body fat. All right, I'm not very creative, so I name my data set something very simple, data. So I want to read.csv, and so I want to access the data, and then I have to attach it so I can perform the analyses on it. I always like to start out with just what's called head of data. It gives me just a glance at the data set. Looks like when we read a data set like this, when we read left or right, we're looking at the cases. So, you know, case number one has the measurements that are given there, and case two and case three, so on. But statisticians were more interested in the variables. And I can see here that I have 4 variables. You may argue that subject number is a variable. I don't think so. But I have a tricep measure, a thigh measure, mid-arm, and a body fat. Now, if I want to find the number of subjects, I can just do length of anything here. I'm just going to choose triceps because it's first. So if I looked at the entire data set, I would have 20 cases, 20 subjects that contributed to, well, that makes up this data. Now, what I want to do here is I want to examine the correlation and regression outputs when predicting, I don't know, let's just predict body fat, which will become our Y because we're predicting it, from, let's just do thigh. All right, so that's the purpose of what I want to do here. In the correlation component, sorry, my buddy's blowing me up on the texting this morning. Correlation, I want to look at 3 things. I want to examine a scatter plot, which is just a picture of the relationship. I want to look at the correlation coefficient, which is my R value, and I want to, sorry, I'm not talented enough to speak and type. I want to look at the coefficient of determination, which is the R squared. From a simple linear regression standpoint, the scatter plot and correlation coefficient are important. Once we move into multiple regression, we'll start to rely more on the coefficient of determination, the R squared. Actually, we'll adjust. We'll focus on the adjusted R squared, but that will come later. All right, gang. Let's do a scatter plot. Very easy. Again, I want to focus just on predicting body fat from triceps. So I will plot. I will need to put my X first and my Y second. Okay, when I evaluate, examine a scatter plot, I'm looking at three things. The focus is, does the relationship appear to be linear? Second, do we have a positive or negative relationship? And third, do we have a strong, weak, or moderate relationship? Now, if I visualize a straight line, if you'll follow my the mouse, if I visualize a straight line, I believe that we do have a linear relationship here. And because when I visualize this line, it increases, it should make sense to you that we have a positive relationship, a positive slope, corresponding with a positive slope. The strong, weak, moderate, very subjective determination comes from visualizing the variation around that line of the point. So again, imagine having a line through the central focus of this data point. How much do these points vary across from, away from that line? If they don't vary much, that indicates we have a strong relationship. We have a tight fit around the regression model. As the points are distributed more, we move into a moderate relationship. As they vary out, fan out even more, we get into a weak relationship. So I would define this as, I'm going to close this down. I would define this as a linear, positive, and strong relationship. Now, what we'll do now is we'll look at the correlation coefficient, which will help us kind of solidify this arguably subjective conclusion. All right, so I can just do correlation. And again, I'm doing thigh over body fat. And the correlation between my X and my Y is 0.88. Just an FYI, if I reverse these, I get the same thing. Now, it doesn't matter with correlation. Now, once we get into the regression model, if I reverse the X and the Y, then I have major issues. So the correlation coefficient, 0.88, indicates a strong relationship. Since it's positive, it indicates a positive strong relationship. So just supporting what we determined by eyeballing the scatter plot. The R squared can get fairly quickly. Literally just squaring the R value. So here we have a 0.77. We report the R squared as a percentage. So the R squared is approximately 77.1%, which indicates that 77.1% of the variance in Y can be explained by the regression on X, which is our thigh measurement. So again, in statistics, you know, regression, we're always trying to explain variation, right? Why do things vary? Why do some people have higher body fats than others? Again, how are we explaining the variance there? So by fitting the regression model, predicting body fat by thigh, we find that 77.1% of the variance can be explained. All right, next thing I'd want to do is, you know, I've kind of checked all the boxes for the correlation component. Again, examine a scatter plot, calculate and interpret the correlation coefficient, calculate and interpret the coefficient of determination. We will now move into the linear regression component. And I begin that by creating a model, and it's easy to do in R, just LM, linear model. I want to predict body fat, so I need to put it first, and I want to predict it from the thigh measure. All right, then I want to do a summary of the model. And for now, you know, first of all, you'll see that the R squared 0.771, the adjusted R squared, that'll be explained in a later video, and then all this, the residual standard error and Now the ANOVA stuff down here, that'll be explained later too. But for right now, what I would do is I would focus on these two values, because these two values give me my regression model. So what I can determine there is that body fat, well, let me restate that. Our predicted body fat can be estimated by taking negative 23.63 plus 0.86 times the thigh measure. So the first subject up here had a tricep of, no, I'm doing thigh, my bad. That would just really be bad if we put the tricep measure in a model that was created from thigh. Anyway, the first subject had a thigh measure of 43.1. We can see that they observed a body fat of 11.9. We can use our model to actually predict the body fat for this particular subject by taking 0.86 times their thigh measure, which was 43.1, and subtracting the intercept, which is 23.63, right? Yeah. So we get a predicted body fat for the first subject of 13.46. So this person's body fat was a little lower than we would have predicted it according to their thigh measure. We expect that variation. We expect a difference in most cases between what the model predicts and what we actually observed. Now, what we can do now, since we've created our model, we can go back and look at our plot, but we can embed the regression model in it. And that's really easy to do. What I would do here is just do width. My data set is data. I would plot x over x comma y, which would be thigh body fat. And then I'm going to add the ab line of my model to the scatter plot. So what I can determine here is, again, for this first subject, thigh of 43.1. 43.1 is down, I guess, about right here someplace. And I can go up to the observed value, 11.9. I can go on up to the predicted value, which would be the value that falls on this point right here. Now let's look at the two subjects with looks like they have a thigh measure of about 50. If I take 50 up to the line, our model is predicting a body fat about 18 or so, anyway less than 20. But what we actually observed with these two particular subjects is that they had a body fat actually higher. One looks like maybe around, I don't know, 21 or 22, and the other, you know, about 23 something. That's okay, and we'll get into describing that difference in just a second. So again, when I first taught this class, I think many moons ago, back in maybe 2013, I found that it'd been a while for most of my students since they'd had a statistics class, or at least some of them, majority. So I just skipped through this stuff last time and kind of got into the good stuff. Well, it's all good stuff, but the harder stuff. And so anyway, I hope this is useful. Now we talked about this difference between. All right, Doug, pump the brakes. All right, the next thing I would want to do is I would want to get the predicted values for all the cases, and I can do that using fitted. So if I get the fitted of my model, what I'm actually getting are the predicted values. And I like to save them. So we determined above that the predicted was 13.436. R is giving us 13.2867. Why the difference? Well, it's just rounding. Now, I used 0.86. R uses 0.8565, and so again, I rounded to 2 places when I made my calculations, so it's going to be off just a little bit. These are better estimates of the predicted value. Now what we want to do is we want to look at the difference between what we actually observe, which is the body fat that we have in our data set, with what our model predicts. And we call these residuals or errors. So a residual is the observed Y minus the predicted Y. So the residual for case number 1, they have an observed Y of 11.9, and they have a predicted Y of, is everybody okay with just 13.3? And if my mental arithmetic is correct, that would be negative 1.4. Now, instead of doing the residuals for each and every case, we can calculate the residuals. And the way we do that is just RESID for the model. And you can see that the residual for the 1.38, which again, I was just approximating here. These are better estimates. Now, if I wanted to, let's say I wanted to get the data set, let's say that I just have tunnel vision, focus on the body fat, the thigh measure, and I want to look at the predicted and the residuals, but I want to create a new data set, just focusing on the variables of interest. So I could create a new data set, let's just call it, and do a data frame. And I could do my thigh, my body fat, what did I call these things? Predicted, and residuals. I can attach my new data, and if I look at new data, what I've done now is I've eliminated tricep and what was the other one? Well, it doesn't matter. Tricep and the other variable. That's going to bug me. What was the other one? Okay, mid-arm. I've eliminated those. Just focus on my X, my Y, the predicted, and the residuals. All right, since I've attached it, I can still perform the analyses on these values. Now, the next thing I'd want to do is address, is a linear model appropriate for describing the relationship between thigh and body fat. So, above we made a subjective determination just by examining the scatter plot, just by eyeballing the scatter plot, that it appeared that a linear model is appropriate. But we need something more significant. And the way we do that is we plot the residuals over our independent variable. So what I would do here is I'm going to plot the residuals. I'm sorry, my X needs to go first. And I'll examine what's called a scatter plot of the residuals. All right. Now, the trick here in determining how meaningful this is, or what it actually means to us and what it tells us, if we have what I call a shotgun blast, where there's no discernible pattern, this indicates that we have that the errors are equally distributed, and that a linear model is appropriate. If we get into a pattern here, and what you'll see sometimes, you'll see a U-shaped, if we see a scatter plot of the residuals over our independent variable that has a U-shape, then it indicates that a linear model is not appropriate. So this plot validates, if you will, the subjective determination decision that we made earlier, that explaining body fat predicted from thigh, or predicting body fat from thigh, using a linear model is appropriate. This graph right here kind of seals the deal, if you will. I really don't, I feel like I'm forgetting something. I probably should have made notes so I don't forget anything, but it seemed like there was something else. Oh, one more thing. We could look at a histogram of the residuals. As we'll find out later, the residuals, if a linear model is appropriate, the residuals will form a normal distribution. Now, again, a normal distribution describes a population distribution. We don't have a population here. We have 20 subjects out of how many hundreds of millions who have a thigh and body fat. Not really sure what our population here is under investigation. In other words, I'm not really sure who we're trying to generalize to. But we can consider these 20 subjects, these 20 cases, as a sample. So when I do the histogram of residuals, and ladies and gentlemen, this is extremely important. You should put in your notes flashing neon lights around this one. When I do a histogram of the residuals, you can see that I get a bell-shaped and symmetric distribution. It is completely, totally inappropriate to call this a normal distribution. Again, normal distributions are specific to population probability distributions. This is a sample. But this sample, which is taken again from a larger population, indicates to me that there's really strong evidence that these residuals come from a distribution that is normally distributed. So when my language is specific to the sample, I can say, yeah, bell-shaped and symmetric distribution. But I can't call this a normal distribution. I can't refer to it as a normal distribution because these 20 subjects don't make up the population. Again, in statistics, our primary goal, almost always our number one focus, is to use sample data to make a statement about a larger population. And that's what I'm assuming that we're doing here. Again, these 20 subjects are hopefully have been randomly selected, and we're using this information to make bigger, broader statements about the relationship between everyone's thigh and everyone's body fat. All right? So again, be careful. It's not a normal distribution. This is a histogram that has a bell-shaped and symmetric distribution. Well, I think that's it. I can't think, I mean, I can think of 1,000 things I could go on and do, but I think we should end here. So take care.